Hello, everybody. My name is Chung. I'm very glad to be here to introduce a revolutionary metal I-fuse technology to you. First, I'd like to give an overview about Attopsemi and then the OTP technology. And then we will present some I-fuse data on 12 nanometer FinFET technology. And then we will compare our I-fuse with the conventional eFuse and also anti-fuse technology, and followed by I-fuse roadmap. Attopsemi was founded in June 2010. It's a pure play IP company. And our headquarters is in Taiwan, Hsinchu Science Park. And we have more than 44 people in different functional divisions. And then we also have a global reps in US, Europe, Israel, and Japan. And we passed ISO 9001 in 2020. We have patents grant more than 90 worldwide, including many in US, Taiwan, China, and European companies. And our technology has been passed AEC 100, grade 0 and beyond. And so far we have our I-fuse work in many different foundries and different nodes, including TSMC from 180 all the way to 12 nanometer. Global foundry 22 nanometer, 130, and some other foundries such as Vanguard, UMC, Micronis, XFAB, and so on. And then our technology can work in bulk CMOS, SOI, and different CMOS derivatives, such as GLP, ULP, and so on, and different type of process, such as high-V, BCD, or CG, silicon germanium. So far, we have more than 150 customers worldwide, and then we offer our IP since 2016, and then we never have any fair return yet. And even though we have many customers worldwide, we have a press release with a few names, such as Vanguard, Global Foundry, ABRIC, NJRC, Fraunhofer Research Institute, Fingerprint Card, Merced, Rambus, and XFAB. I'd like to introduce a little bit about different OTP technology. The older one is called logic EEPROM. It's a use logic process to do the E-square PROM function, and by storing the charges in 14 gates. And then since charging might leak away, so that there's always a data retention problem. And the next one is anti-fuse. And when the technology go beyond 180 nanometer in the year 2000, and then oxide breakdown voltage can be lower than the junction breakdown voltage. So that some clever engineer figure out a way to create OTP by deliberately break the oxide. However, once rupture oxide may appear to be here by itself again, and because there could be the soft breakdown associated, which means it's not really the hard breakdown. The oxide actually didn't get totally ruptured. And another one is the eFuse. It almost happened everywhere. It happened in foundry, IDM, or even fabless. The concept is very simple, and people just try to get a conductor, and used to be silicide poly, and later on could be metal, and then they just apply high voltage and introduce a very high current and to break it. And then this is an explosive type of behavior. And then the broken eFuse and then can appear to grow back after use for a long time or after burn-in. And finally, we'd like to introduce our I-fuse. Is a non-explosive fuse technology. The programming is deterministic, and then can work from 0.5 micron all the way to 12 5, 3, or even 2 nanometer. And then so far, we haven't seen any problem yet. I'd like to spend more time to talk about the fundamental I-fuse mechanism. And then the view graph shows IV characteristics of a fuse. And then when we apply the voltage and there was current flowing through a fuse, since the fuse is a conductor. And then the inversion of the slope when the voltage is very low is called initial fuse resistance. And as voltage is higher, more current will flow through. And higher current will create your heat to raise the temperature. So the fuse resistance will be increased. And then the curve will be bent toward the x-axis until to a point we call critical point. Then after this point, we have a small increment in voltage. However, current drop. So this is not going to happen to any conductor unless this conductor is broken. And people always think they need to break the fuse so that they can enjoy the very high resistance forever. So everybody thinks they need to apply voltage higher and now and to go beyond this critical point. And as you can see, we just show 3 different fuses. And then they all behave differently in the beyond the critical point. As a matter of fact, beyond the critical point, the program behavior is more like an explosion. And after explosion, debris can be created and can micro bridge again and become short. And this becomes a serious reliability issue. On the other hand, our I-fuse program is below the critical point and then above the electro-migration threshold. So all 3 fuses show similar kind of behavior. As a matter of fact, if I have a chance to show you 3 million or 3 billion fuses, the line segment between the EM's ratio and critical point will be all the same. They just follow very nice, smooth curves. So our I-fuse programming is deterministic. It's controllable and can be modeled by physics. And then the overview of the SEM below further confirm our electrical theory. For eFuse, other programming, we are going to see a big hole got blown up in the fuse body. However, for I-fuse, and then the program status is almost invisible. And there's a more profound meaning of the critical point. In 2016, we published a paper in IEEE conference. We proved the critical point is the beginning of thermal runaway. Because if the current is higher enough, can create geoheat and to raise temperature, so that fuse resistance will be increased, and then the more heat will be generated. And if we keep pumping more and more current, eventually the heat generated by the fuse body can be more and the heat can be lost to the environment. Then at that time, thermal run will happen, which means the temperature can be as high as possible. As a reality, temperature is meaningless because the fundamental law of conservation of energy breaks down. And for some of you may have some experience with power device before. We all been taught by guru in the industry or by the textbook that the power device should not operate in thermal runaway to be reliable. So if that's the case, we shall program a fuse like an I-fuse way. And this view graph shows minimal program current of I-fuse in different technology. And then from 0.35 micron all the way to 40 nanometer, we use silicide poly, and then the program current can be scaled. And then for 22 and 28, we'd like to use metal gate technology. And the program current is very low too. And then for 12 nanometer and beyond, we prove metal can be a very good material for I-fuse. And then it can be scalable because the metal dimension can be scaled as technology goes. And then so that the program electro-migration threshold will be scaled down, and the minimal program current can be lower. And then so that the metal I-fuse can be workable to 2 nanometer and beyond. This view graph shows more data of 512 by 8 and 20 nanometer technology. And then we try to test if OTPs can be programmed, and then by incrementing the program voltage from 1.64 all the way to 2.5, we find out our program window can be pretty wide from 1.7 volt all the way to 2.5 volt. And then the view graph on the left further show the cell current distribution. The blue curve shows the cell current before program, and then the current is pretty high. And then the left one, the green one, shows the program current of the program. And then the current is very low since the fuse resistance become very high. And then as you can see, it doesn't matter on program or program cell, and then the distribution are pretty narrow, and then the separation between data 0 and 1 are pretty wide apart. And then this view graph further shows the program current. We try to program a bit, and then use a current prop and to capture the waveform in the scope. And as you can see, the program time is less than 2 microseconds. And then the peak program current is less than 14 milliamp. So the programming is pretty nice and one shot only. We don't need any read back and reprogram mechanism like in the anti-fuse. And then there's a unique characteristics of our I-fuse is called fully testable. And because field return is very costly, so we want to have a zero defect. Otherwise, if a defect got caught in the later stage of the system, and the cost is 10 times. However, OTP is inherently very hard to be very hard to be tested. There's a OTP dilemma. Ideally, we want to fully test every OTP bit before shipping. Otherwise, how can you guarantee every bit can be programmable? But however, if you just program a single bit, this OTP macro cannot be used anymore. So it's a dilemma. In English, there's a saying, you cannot have the cake and eat it too. And then another issue is if you take a brand OTP and to read the data out, it's all 0 unless you program it. And then if the data is all 0, you cannot detect any stack at all. However, our I-fuse can solve all the problem because we can guarantee our I-fuse cell can be programmable without actually programming. And because our program mechanism is based on heat accelerate electro-migration. So if we can test and screen if the initial fuse resistance is very low, less than 400 ohm, for example. So we can guarantee this cell can be be used to generate enough heat to be programmable. The second thing is there's always yield loss for the eFuse or anti-fuse. But however, for our I-fuse, we can guarantee almost 100% of program yield because we test a program and try to find the program window. And then once we find the program window, and then we just suggest to our user to program in the middle of the program window. So as long as the user can follow our guideline, and we can guarantee our I-fuse cell can be almost program yield 100%. And finally, there's another tricky part. One of our customers would like to have a fully testable for every functional block, including OTP cell, OTP array, XY decoder, control logic, or even program circuits. And we invented a very unique scheme to solve the problem. We create a non-destructive fake reading one state. So that by combining this fake reading one state with the normal reading zero state. So we can generate SRAM like a test pattern to have a fully exercise, almost 100% coverage, such as a complicated match pattern and so on. And the implementation level is we try to read a cell, and at the same time, we also apply low voltage to fake or program this cell. And then by doing this way, the binary voltage will be pulled high so that the sense amplifier will consider this cell pretty much like have a high resistance. And then the output data 1. And our I-fuse has many advantage. For example, small size, because we don't need the high current to program. And then so the size can be smaller. And then because we don't break it, so that the program voltage can be very low. And reliability is very high because we don't go beyond the thermal runaway. So this high reliability is guaranteed by physics. And for example, we have many projects qualify beyond the ASIC Q100 grade 0. And then, after so many IP offered to the customers, we find out natural defect is less than 1 per billion. And then we can easily pass more than 300 degrees C for high temperature storage. And then since the damage to the fuse is very minor, so we have very wide temperature operation. We can work at -55 all the way to 150 degrees C or beyond. And it's very good for automotive application. And finally, we talk about the fully testable. We can generate non-destructive tester to screen the virgin I-fuse, and then also the fully test every functional block. So even though there are many OTP programming mechanisms out there, we offer the only OTP programming mechanism that can be modeled by physics. It's based on heat generation, heat dissipation, and electro-migration. We'd like to compare our I-fuse versus eFuse at 22 nanometer nodes. And for example, our I-fuse at 22 nanometer, 32K bit IP size is even smaller than conventional eFuse at 28 nanometer and then just 4K bit. And then our programming current can be less than 3 milliamp. However, eFuse need to have more than 100 milliamp. And then our I-fuse can easily pass 250 degrees C for 1,000 hours, and then with 256 kilobit in a single texture without any redundancy. However, I-fuse just merely 4 kilobit. They can pass 125 degrees C for 1,000 hours, but they need to have a twin cell, which means they use 2 cells per bit. And then the eFuse has limited read time, and then always have program yield loss and not scalable and not testable. However, I-fuse can have almost unlimited read time, and then almost 100% program yield, and then fully staticable, and then fully testable. And we'd like to compare with anti-fuse tool. As technology goes, more and more advanced, and then fuse will be narrow, so that the electron-migration ratio will be lower, and then the program current will be lower, and then so that the program current can be reduced. And then in the end, our I-fuse is scalable from 12 to 7, 5, 3 to 1, because the metal width and metal height is a scale according to Moore's law. And then our non-explosive I-fuse will win over the explosive eFuse. On the other hand, for anti-fuse technology, they count on high voltage to break the gate oxide, but the gate oxide thickness cannot be scaled when the technology go beyond 40 nanometer. And then so that the program voltage cannot be scaled. For the anti-fuse at 5 nanometer nodes, the program current is still about 5.4 volts. Cannot be scaled much, almost the same as like 40 nanometer nodes. On the other hand, nanometer device just cannot be sustain high voltage anymore. So in the end, the device will break down before the oxide rupture, so that the anti-fuse will be very hard to work beyond the 16 nanometer. And people need to spend a lot of time to play all kinds of tricks, to use a voltage divider to reduce the voltage applied to each device and so on. It's a very painful process. So the conclusion is fuse is a current programming will win over the anti-fuse voltage programming. And even for the current programming, non-exposed I-fuse will win over the exposed eFuse. And this is our I-fuse roadmap. And we have a IP offering from 0.5 micron all the way to 12 nanometer. And we are working with our partner customer on 7, 5, and 3, and so on. And the conclusion is our I-fuse is a non-exposed fuse-based OTP. And because our programming is below thermal runaway, and then about the electro-migration threshold. So that electro-migration will be the sole programming mechanism. And then actually our programming is just apply heat to accelerate natural logic device aging by electro-migration. And we all know that electro-migration is an irreversible process. So the reliability is guaranteed, not by us, is by the physics created by Almighty God. And then our I-fuse material can be CSI poly from 0.5 micron all the way to 40 nanometer, and can be metal gate from 28 to 22, and then can be metal I-fuse from 60 nanometer and 2 nanometer and beyond. And then our I-fuse is testable because our I-fuse is a logic device. So we can create a non-destructive to test the program state by just screening the resistance of virtual I-fuse. And then we can also create a non-destructive fake program state so that we can fake one, and then by combining with a normal read 0 to generate a very complicated SRAM like test patterns. So in the end, our I-fuse is scalable because of metal width and height, it can be scaled as technology goes. And then so that the program current can be scaled, as width and height scale. And then program voltage will be reduced. And then so that our I-fuse based on metal can be ready to go to 7, 5, 3, and 2, and even beyond. Thank you very much for your attention.